In the late 1630s, the French jurist and amateur mathematician Pierre de Fermat enunciated what has come to be known as his famous last theorem. On June the 23rd, 1993, Professor Andrew Wiles of the University of Princeton, lecturing at the Newton Institute in Cambridge, claimed that he had proved this notorious result. What I would like to do in this talk is to give a brief history of the attempts that have been made to solve this problem, and to very briefly outline some of the ideas that have led into Andrew Wiles's attempted proof. Pierre de Fermat wrote in the margin of his copy of Bachet's edition of the works of Diophantus, which I have here a life-size copy of, he wrote, "It is impossible to separate a cube into two cubes, or a biquadrate into two biquadrates, or in general any power higher than the second into powers of like degree. I have discovered a truly wonderful proof which this margin is too small to contain." From that day to this, no one has been quite sure what the proof was that Fermat claimed to have found. All we know is that it has to fit into the margin of a book which is 2 inches by 10. Now, in modern notation, what Fermat claimed was that x to the n plus y to the n equals z to the n has no solutions in non-zero integers x, y, and z when n is greater than 2, and it is this assertion which is known as his last theorem. Fermat's theorem covers the equation in the case when the exponent n is greater than 2, but first I think we should study the case when the exponent n is equal to 2. In this case, it is well known that there are solutions, the simplest of which is 3 squared plus 4 squared equal to 5 squared, and this particular relation has been known at least since the time of the ancient Babylonians, and so is probably one of the oldest arithmetic facts in history. What Diophantus had actually proved in the book in the margin of which Fermat had been writing was that the general solution to this equation can be expressed in the form x equals u squared minus v squared, y equals 2uv, and z equals u squared plus v squared for any integer values u and v. It can easily be verified simply by substituting these into the equation that this is a solution, and what Diophantus had proved was that these are the only solutions. Now, Diophantus' approach to this was to consider geometrically what it means to have an integer solution to this sort of equation. So, an integer solution to an equation of the form u to the n plus v to the n equals w to the n, on dividing through by the denominator w, is a rational solution to u over w to the n plus v over w to the n equal to 1. That is, it gives a rational point on the curve x to the n plus y to the n equals 1, where where x, of course, is u over w and y is v over w. Now, in the case n equals 2, the equation is the equation of a circle, and if we have a point xy on the circle, let us suppose that the angle subtended at the center is theta, so the angle subtended at the circumference is theta over 2. Now, if we put t equals tan half theta, so that x is cos theta and y is sine theta, then using the tangent of the half-angle formula from elementary trigonometry, we find that x is 1 minus t squared over 1 plus t squared, y is 2t over 1 plus t squared, and substituting t equals u over v gives the equation that Diophantus had originally found. Now, we're interested in generalizing this to the case when n is greater than 2. So, for example, here is a sketch of the curve when n equals 3. For odd exponents such as 3, the curve no longer has circular symmetry, but instead goes off to infinity, asymptotic to the line y equals minus x. And the assertion of Fermat is that this curve has got only the rational points in which one of the two coordinates is 0. Now, I said that Fermat gave no hint of what his general proof was, but we do know that he had a proof in the case n equals 4, and this proof was based on the studies of Diophantus. So I'd like to begin by outlining Fermat's original proof. So if in the 1630s, Fermat proved that his theorem holds for the case of exponent 4, and in fact what I'm going to do is to show that there is no solution to the equation x to the 4th plus y to the 4th equals z squared, in which x, y, and z are all non-zero. Fermat's technique for solving equations of this form he called infinite Dissent. The idea is to suppose that there is a solution in which x, y, and z are all non-zero. We assume that this is the smallest solution, in other words, that the value of z is as small as possible, and by algebraic manipulation we derive a solution in which the value of z is even smaller. Since z is a non-zero integer, and since there can be no infinite descending sequence of non-zero integers, since there is a smallest non-zero integer, namely 1, we conclude that the supposition that there was a solution in the first place is untenable, and show that the equation has no solutions. So let's follow through the algebraic manipulation. We write the equation as x squared squared plus y squared squared equals z squared. This is now in the form that Diophantus had found a parameterization for. We assume that x is odd and y is even. Then x squared must be expressible in the form u squared minus v squared. Y squared must be expressible in the form 2uv, and z must be of the form u squared plus v squared. We can assume that there is no common factor in u and v, since a common factor in u and v would be a common factor in x, y, and z, and we could divide through by it. And then the fact that 2uv is a square, and u and v have no factor in common, means that u must be a square, say p squared, and v must be a square, twice a square, say 2q squared. So our original equation becomes x squared plus 2q squared, all squared, equals p squared squared. And now this is again in the form that Diophantus had treated. We can write x as a squared minus b squared, 2q squared as 2ab, and p squared as a squared plus b squared, where again a and b are integers. Again, we can assume they have no common factor, since a factor in common between a and b would again give us a factor in common between x, y, and z. It turns out that a must be odd and b must be even. Now 2ab is twice a square, so a and b must both be squares, say a equals c squared and b equals d squared, and we show that c squared squared plus d squared squared is equal to p squared, where it's now easy to show that p is less than z. So the assumption that there is an equation with right-hand side z non-zero and as small as possible is untenable, and so there can be no solutions to the original equation x to the 4th plus y to the 4th equals z squared with z non-zero. And this is sufficient to prove the case n equals 4 of Fermat's last theorem. Since every exponent must be either divisible by 4 or by an odd prime number, we can assume that the exponent is a prime number, say p. The next advance was made by the Swiss mathematician Euler, who tackled the case n equals 3. His proof was not complete it was in fact not completed until 1822, when the German mathematician Karl Gauss was able to fill a gap in an assumption that Euler had made about factorization of numbers that involve the cube root of unity. Gauss, who completed the proof in 1822, was one of the giants of mathematics. It was said that he was the last person to understand everything in mathematics, and that after his time that was impossible because he had advanced the subject so much and in so many different ways. He was the court mathematician and astronomer at the University of Göttingen, and he had already made significant advances in the theory of numbers while still a teenager. Indeed, it is said that one of the perils of working in mathematics in the early 19th century was that everything had been done by Gauss while still at school, but he had not thought it interesting enough to publish. In the case of Fermat's last theorem, Gauss's expertise seems to have slipped. He thought that the problem was not very interesting and said that he could conjecture an infinite number of similar problems, the resolution of which would be equally uninteresting. This seems to be the only occasion on which his eye for a good problem failed him. Gauss cleared this up in 1822. In 1825, Dirichlet attempted to extend this working to the case when the theorem with exponent 5. There was again a difficulty which he resolved in 1828. In 1839, Lamé, by a similar analysis, managed to prove Fermat's last theorem for the case of exponent 7. And as you can see, the gap is getting wider, and it was clear that this line of argument was going to lead to considerable difficulties. The subject was finally resolved by Kummer, who was able to resolve the problem of the factorization in a study which led to the foundation of the modern theory of algebraic numbers, and which showed that the line of argument started by Euler in fact had no chance of succeeding in general, and that completely new methods of argument were going to be required. At this point, it's convenient to split the theorem up into two cases. We shall say that the first case holds if there are no solutions in which x, y, and z are all prime to p, and that the second case holds if there are no solutions with one of x, y, and z divisible by p. So Fermat's last theorem will hold if it holds in both the first and the second case. Now, under the Napoleonic regime in revolutionary France, it was decided that what an army officer needed in order to prepare him for military service was a thorough education in mathematics, and the École Polytechnique was formed in order to provide officer cadets with the training they required. One of the lecturers at the École was the mathematician Joseph-Louis Lagrange. In 1804, he was communicating with a young student who wrote to him under the name of Monsieur Leblanc. Monsieur Leblanc wrote to explain that he was unable to attend Lagrange's lectures, but he had been conducting independent research and would value Lagrange's opinion on his manuscripts. Lagrange read the manuscripts and was very impressed by the young student's researches. He asked to meet him, and after a complicated series of negotiations, he finally went to the student's home and was very surprised to be met not by the young Monsieur Leblanc, but by Mademoiselle Sophie Germain, who, as a woman, was debarred from army service and therefore from entry to the École Polytechnique. Nonetheless, she had been able to obtain Lagrange's lecture notes and to start research in number theory. She had obtained some results in the direction of Fermat's theorem, and it was the first case which she had been studying. In 1808, she proved that the first case holds for exponent p if 2p plus 1 is also prime. This covers, for example, the case p equals 3, since 7 is a prime, already proved by Euler, the case p equals 5, since 11 is prime, but does not cover the case p equals 7, since 2p plus 1, which is 15, is composite. Working with the mathematician Legendre, she was able to extend her analysis, and by 1823 they had proved that the first case holds for exponent p if kp plus 1 is a prime for k equals 2, 4, 8, 10, 14, or 16. This already suffices to show that the first case holds for all exponents up to 100, and this was achieved by 1823, which was before Dirichlet had given his proof of the full theorem, even in the case of exponent 5. Gauss was very surprised when he heard that Monsieur Leblanc, who had already started to correspond with him under the pseudonym, was in fact Mademoiselle Germain, and wrote, "How can I describe my admiration and astonishment at seeing my esteemed correspondent metamorphose into this illustrious personage? A taste for the abstract sciences in general, and above all the mysteries of number, is excessively rare. One is astonished. The enchanting charms of this sublime science reveal themselves only to those who have the courage to go deeply into it. But when a person of the sex which, according to our prejudice, must encounter more difficulties, succeeds nevertheless in surmounting these obstacles and penetrating the most obscure parts of them, then without doubt she must have the noblest courage, quite extraordinary talents, and superior genius." Now, the first case was picked up by Wieferich in 1909, who proved the following very valuable criterion. The first case holds for exponent p if p squared does not divide 2 to the p minus 2. Lehmer showed by direct calculation that the only primes p up to 6,000 million which do not satisfy this condition are 1,093 and 3,511. The Wieferich condition was later extended by van Diver in particular to show that the first case holds for exponent p if p squared does not divide one of the numbers b to the p minus b for b less than 100, and Granville in 1988 was thereby able to show that the first case holds for all p less than 156,442 million. Now, progress on the second case was much slower, but using the work of Kummer, van Diver, Stafford, the Lehmers, Wagstaff, and Buehler were able to prove that Fermat's theorem holds for every prime up to 1 million. The value of this computationally was shown by Inquiry, who proved in 1953 that if x, y, and z form a counterexample to Fermat's theorem, then x must be at least a number which is slightly less than p to the 3p, and since we know that p must be at least a million, if x, y, and z form a counterexample to Fermat's theorem, then x must be at least 10 to the 18 million, a number of nearly 20 million decimal digits, and so we know, in particular, that any number that could be written down in a convenient space of paper, such as the margin of Bachet's edition of the works of Diophantus, cannot possibly be part of a counterexample to Fermat's theorem. Now, this was the end of the line for computational problems. In 1985, Roger Heath Brown showed that the first case holds for infinitely many values of the exponent p, and in the same year, simultaneously with Andrew Granville, he showed that Fermat's last theorem is true for almost all exponents n, in a certain technical sense of the phrase almost all. That's to say, if an exponent n is written down at random, then the probability is 1 that Fermat's theorem is true for that exponent. Now, in 1908, one of the biggest disasters to befall the theory of numbers occurred when the late Dr. Paul Volscale of Darmstadt, by his will, bequeathed the Volkscale Prize for the solution of Fermat's last theorem. He wrote that the Academy at Göttingen was to decide to whom the prize was to be conferred, that it was to take into consideration memoirs, monographs, or books, and that the value of the prize would be 100,000 Reichsmarks in gold. Although the value of the prize was destroyed by the Weimar inflation, it has since recovered to about 15,000 Deutschmarks, roughly £5,000, which is still worth having, and immediately the prize was announced, the University at Göttingen was besieged by claimants who wished to claim the Volkscale Prize. The university had printed postcards which were issued to graduate students saying, "Dear Sir, thank you for your solution to Fermat's theorem. The first mistake in your manuscript is on page blank, line blank," and these cards were to be filled in by the graduate students as the manuscripts arrived. In this country, the University of Cambridge is one of the lucky recipients of the attentions of the amateurs who wish to claim the Volkscale Prize, and I have had the dubious privilege of reading some of these. I was particularly amused by the claimant from China who wrote to explain that it would be necessary for me to attend his lectures on his proof in person, and would I kindly send him an airline ticket for himself and his mother so he could come and explain the proof to me. When I wrote to decline the honour, he replied saying that it wouldn't be necessary for me to send the airline ticket for his mother. We have also had a number of claimants who are quite willing to resign the honour of the prize for a share of the prize money to be paid to them, of course, in advance. Finally, we turn to the work of Andrew Wiles, the person who seems most likely to actually win the Volkscale Prize, and in order to understand his work, it is necessary simply to make the definition of the genus of an algebraic curve. We say that a curve has genus 0 precisely when it is a conic, for example, a circle, an ellipse, hyperbola, parabola, and so on. A curve has genus 1 when it's a plane cubic, which can be written in the form y squared equals cubic in x. All other curves have a genus which is greater than 1. Now, the relation to Fermat's theorem is through the conjecture of Taniyama, Shimura, and Weil, who claimed that every curve of genus 1 is modular. I don't propose to explain what modular means. It means that, very roughly, that the curve has got a number of points when considered modulo every prime, which is predictable in a certain way. One can think of modular curves as being the good ones. The Shimura-Taniyama-Weil conjecture is simply that there aren't any bad ones. The relationship to Fermat's theorem was found by Fry and Ribbit in the 1980s. They showed that if the Shimura-Taniyama-Weil conjecture is true, then Fermat's theorem is true. And the way they proved this was to consider a solution to Fermat's equation, say u to the p plus v to the p equals w to the p. Then the equation y squared equals x into x minus u to the p x plus v to the p is a cubic curve, and therefore of genus 1, and it's possible, quite simply, to show that this is not modular. So if there is a counterexample to Fermat's theorem, then the construction of Fry gives a counterexample to the Shimura-Taniyama-Weil conjecture. And what Andrew Wiles claimed in 1993 was that every curve of genus 1 with a condition called semi-stable reduction, a condition satisfied by the Fry curve, is indeed modular. In other words, he claimed to have proved most of the Shimura-Taniyama-Weil conjecture. And from this, it is possible to deduce that Fermat's last theorem is true. Now, I've put a question mark against the date of the proof, and the reason for that is that while he announced his proof and gave some of the details, it is not at present possible to be sure that his proof is complete. The details were circulated to a handful of mathematicians in late 1993, And unfortunately, one of them discovered that there was a gap in the proof of a technical part of the proof. And while this gap is said by experts, among whom I do not include myself, by the way, to be easy to fix by the usual methods, nonetheless, the proof has not yet been completed, and at present it is unfortunately true to say that there is no proof of Fermat's last theorem. Nonetheless, the advances made by Andrew Wiles are truly significant. There is a considerable amount of optimism among the experts that the gap can be filled, and it is to be hoped that in the very near future we will be able to see a complete and correct proof at last to this 350-year-old last theorem of Fermat.